Hi everyone, this is the video for discussion section 10. So we'll be talking about phase diagrams, but before we get into the new material, I wanted to talk about some of the logistics stuff because I know that we've made a lot of changes in the last couple weeks, because we've had to, but I just wanted to go through some of those changes and make sure we're on the same page. Also, this week's discussion section is going to be in 2 videos. I just thought it would be easier for you guys to be able to split it into 2 videos more easily. So this video, I'm going to be talking about some logistics of participation, the final, etc., and then a review of some of the energy balance concepts. And then in the second video, which will also be linked below so you can find it easily, I'll talk about phase diagrams. Okay. So logistics stuff, one small thing I wanted to say is that Dr. Assistant sent out an announcement about this, but we do have the physical copies of your midterm exams. A lot of you were able to pick them up in person after the exam, and some more of you have requested scans, but we do have those. So if you want a scan of your midterm, please contact your GSI. So I have sections 101 and 102's midterms, and Elise has the other 2 sections midterms. And if you have any questions about those, why you lost points, or just sort of want to discuss, we're obviously very happy to do that. There have been a lot of questions about lecture participation and attendance points for discussion. So I hope we've clarified that, but just to sort of reiterate, what we're going to be doing is we will have assignments on B courses that you'll have to submit, something for participation in lecture and also something to get marked for attendance for discussion. So what we've pretty much settled on is for lecture, that will be something that's a little more involved. So it'll be kind of like we would usually do, where you work on solving a problem or jot down ideas to show that you're really engaging with what's going on in the lecture. Whereas for discussion, we really just want you to be here. So it'll be a question that's much more like, you know, if you watch this video, you will know that the second problem was about heating a house or something. So it will be more like 5 words just sort of to prove that you watched the video. So I hope that that won't add really any amount of time at all to your study time for this class. We just want to give you credit for having engaged and having watched these videos. You don't, because you're submitting it via B courses, it's already associated with your name and section and everything, so you can feel free to just write your answer to the question, and that's all you need. Yeah. So for the final, thank you all for filling out that form. If you haven't yet, it's still on B courses. We would love for you to fill it out. Dr. Assistant talked about this in lecture this morning, but as we expected, there's a lot of people in various time zones across the world and who have spotty internet and sort of a whole wide range of things. So I just want to reassure you, we haven't fully decided exactly how that final exam is going to function, but I don't even have a printer at my house, so we wouldn't expect you to be able to print an exam, solve it, and scan it and get it back to us in 3 hours. So, don't worry about that. Please just fill out that form and we'll be as accommodating as we can. Absolutely no one will have to take the exam at 3 a.m, or, in Ramadan times that don't work for them, or, no one will get kicked out of the exam because they have spotty internet. So please don't worry about that. We'll keep you guys in the loop, but we're definitely going to be as accommodating as possible on that exam. I also wanted to say in general, I hope that all of you are healthy and your families are doing well, but I recognize that, you may get sick, your families may get sick, you may not have internet at your house, sort of any wide range of things can happen. We're in the middle of a global pandemic. So this class should really not be the most stressful thing going on for you right now. And if it is, please talk to us. If you email us and tell us you're sick or your mom is sick or whatever, we're very happy to give you extensions on things or give you whatever help you might need. So please just talk to us. We really want to be understanding and helpful and help you guys get through this. We can't do that if we don't know what's going on with you. So just email us or call us, whatever. We'll figure it out, and we really want to help you pass this class. And then the last thing on logistics is there have been a lot of questions about, given that pass, no pass is optional, should you pass, no pass this class or your other classes? And the answer is I don't know. It's complicated depending on what your situation is. But a couple things I will say. One is admissions. If you're thinking about applying to grad school or med school or whatever else down the road, I guarantee you admissions departments are going to be very understanding about this. I know that the College of Chemistry here, where, just as an example, because you guys won't be applying to grad school here, but has made an announcement that, anyone having pass, no pass grades during this time, they'll be totally okay with that. So I do definitely want to normalize you taking advantage of that pass, no pass option. You should feel totally free to do that, especially for a lower level class like this. If you apply to PhD programs in chemical engineering and have grades for CBE40 and 141 and transport and all the later classes, they're not going to be like, oh, but you pass, no pass CBE40, you clearly don't know how to do mass balances. So I really wouldn't, absolutely nothing bad will happen to you for having pass, no pass this class. That said, you will end up with a GPA at the end of your 4 years, obviously. And, if I were in your shoes and got a 95 on the midterm and felt pretty confident that I was going to be able to get an A in the class, there's an argument to keeping the letter grade just to boost your GPA later. But, if it were me taking this class as a student, I would be pass, no passing everything, because I really think there's no downside and you really don't need extra stress of worrying about letter grades right now. So whatever works for you, whatever you want to do, you should feel totally empowered to do that. And also feel free to talk to us if you want advice. But yeah, I don't see there being any negative consequences of pass, no passing. I think everyone kind of understands that it's a crazy situation. Okay, so that was all I wanted to say about logistics. So now I'm going to move into a review of energy balances. So this is our general balance equation. We've talked about it mostly for mass, but it also applies to energy. So you should be pretty comfortable with this. Accumulation equals in minus out plus generation minus consumption. However, for energy, it can't be generated or destroyed. It can't be created, so that generation term has to be 0, and it can't be consumed. The total energy can't be consumed, so that consumption term has to be 0. So for energy, it's pretty safe to say accumulation equals in minus out. So then what does energy actually look like? It really comes in 2 forms. The change in internal energy, which is just sort of, all that means is that we're not worrying about potential energy. We're not worrying about our chemical reactor is on a train and has some kinetic energy because the train is speeding up. We're really worrying about the internal energy of the actual species in our system. So, I'm sure in your physics classes, you've spent a lot of time on potential energy and kinetic energy. We might reference that in passing, but really this class is not about a reactor falling out a window and, losing potential energy or anything like that. So U is that internal energy, and then Q and W are heat and work. And I want to remind you, we've talked about the sign conventions on Q and W. So Q is heat into the system. So Q is greater than 0 if we're adding heat into the system. So, you know, our reactor is on a heater and is having heat provided into it. And that sign convention is pretty universal. And then W is the work being done on the system by the surroundings. And that sign convention switches back and forth. And it really doesn't matter which sign convention you use, provided that you're consistent. So the one that I like, and the one that we are generally using, is that W is the work done on the system. So W is positive if something is doing work on the system. And that just makes sense to me, that things are positive when they are causing the energy of our system to go up. But some people say that W is the amount of work your system does on the surroundings, and you know, that's fine. But this is what I sort of stick with. Okay, so then how do we account for changes in our system? How does that affect our energy balance? So if we don't have a phase change and we just have a temperature change, then we're going to have delta U equals M, so the mass in question, the heat capacity, which is C. We have either CP or CV. So CP is the heat capacity at constant pressure, and CV is the heat capacity at constant volume. Pretty often we use heat capacity we use heat capacity at constant pressure, because, you know, that's sort of the most common situation, is that our volume isn't constrained, but we're sort of in a room at atmospheric pressure, so our pressure is 1 atmosphere. But that's just something you have to judge based on what you're given. Often CP is the same as CV, and on what situation you're in. And then temperature, so the delta T. And delta means final minus initial, so the final energy minus the initial energy equals M times the heat capacity times the final temperature minus the initial temperature. And then if we have a phase change, that delta U equals the mass of stuff that undergoes that phase change times the delta H of the phase change. And that delta H is something that you're going to be given or going to have to look up in a table. So the delta H of vaporization and the delta H of melting are positive. There's, to me, 2 easy ways to remember this. One is that I talked about in my other energy balances video, where I was going through the homework, is the example that I always think of is that the reason that we sweat is that water on our skin, when it goes from the liquid phase to the vapor phase, so when it vaporizes, it absorbs some amount of heat. So it absorbs heat, its delta H is positive, which cools us down because it's taking that heat from us. And so when we go from a liquid to a vapor, that delta H is positive. And then I just think that, you know, melting is analogous, that we're going from a more solid thing to a less solid thing. Another way that works for some people is just thinking about looking at an individual molecule. So in a liquid, in a condensed phase, those molecules are moving a lot less than they are in a vapor phase. And so the fact that they're moving more, bouncing around more, probably means they have more energy. So sort of however you want to think about that to justify delta H of vaporization and delta H of melting being positive, whatever works for you. But don't memorize it. You should be able to sort of logic that out for yourself. And then delta H of condensation is going from the vapor phase to the liquid phase. So it's the opposite of vaporization. So if you're given delta H of condensation, you should be able to get delta H of vaporization and vice versa just by switching the sign. And then delta H of fusion, which is the same as delta H of freezing. So you're going from a liquid to a solid, is the same idea. It's the negative of delta H of melting. Okay, so I wanted to do one example problem on this. So this is 3.62 from the book. So we have a stream of F, G, and H, which is heated to separate F vapor from G and H liquid. So we have 20% F, 10% G, and 70% H. at 20 degrees C going into this heater. Some heat is provided. That's what we need to find. We need to find how much heat is provided to then have F as a vapor and G and H remaining as a liquid. So we have some properties listed down here, and we can use that to find Q heater. If you want extra practice with this, I think this is a good problem to practice, so you can pause this video if you would like and try to practice this. I'll give you a second to do that if you want. If you want a hint before you want to pause and practice, you'll notice that the boiling point of G and H are 176 and 197, so we're not anywhere close to that. So what's going to happen to G and H is they're both going to need to be heated as liquids from 20 to 110. There's no phase change involved there. F, however, has a boiling point of 105. So it needs to get from 20 degrees C as a liquid to 110 as a vapor. So as a liquid, it heats to 105, then it vaporizes, and then it heats from 105 to 110 as a vapor. So if you want to now pause and try to practice, you can. In just a minute, I will go ahead and solve it for you. Okay, so I'm gonna switch to the Notes app. Okay. So here's just the problem again, but smaller, and we're gonna try to find Q heater. So, like I said, G and H need to go from 20 to 110 degrees C as liquid, and F needs to go from 20 to 110 degrees C as a liquid. Sorry, it needs to go from 20 to 105. Then it needs to vaporize. And then it needs to go from 105 to 110 as a vapor. Okay. And so the delta H of F and G and H are all going to be positive. They're gaining heat. And that means that Q heater needs to be positive, that it's that heater that is providing the heat. So everything we do here should be a positive number. Nothing is losing heat. Okay. So if we write that out just in variables, we're going to get that Q heater equals the flow rate of G times the CP, the heat capacity, of G as a liquid times the temperature change for G. So that is 110 minus 20. And we can do the same thing for H. (110 minus 20). And then the last thing we need to do is account for F. So we're going to have the flow rate of F times, and then everything that happens to F is going to be times that flow rate. So we can just pull out that flow rate before we even get into it. Then we're going to have CP of F as a liquid. And what's happening to it while it's a liquid is it's going from 20 to 105. Sorry, I can't talk and write at the same time. So final temperature is 105, initial temperature is 20. Then it needs to vaporize. And then, now that it's a vapor, it needs to heat to 110. So we're going to have CPF as a vapor going from 105 to 110. Sorry, that's not that clear. Okay. And so then all we have to do is plug in our values. One thing to be a little bit careful of is units. So we're lucky here. CP was given to us in kilojoules per kilogram, and all of our delta H's were also given to us in kilojoules. But our magnitudes of CP and delta H are pretty different. So it's actually pretty common for delta H to be given to you in joules, while CP is given to you in kilojoules. So that's just something to keep an eye on. It's a really common mistake that people keep their CPs in kilojoules, or keep their CPs in joules and leave their delta H's in kilojoules, and then you get the wrong answer because you've mixed units. So just as a caution, keep an eye on that. Okay, so I'm gonna try to keep that physical properties table in the window. So then Q heater, our flow rate of G, we can find up here. We have 10 weight percent G, and it's 100 kilograms per minute of our total stream. So that means our flow rate of G is 10 kilograms per minute. Our heat capacity of G as a liquid is here. So that is 2.0. And then we're going to multiply by 110 minus 20. And then we're going to do the same thing for F. So our flow rate of F, we have 20 weight percent F and a total of 100 kilograms per minute in that stream. So if we multiply those, we'll have 20 kilograms per minute of F. Its heat capacity as a liquid we can find here. So that's 1.6. And then again, we should be doing H. That is my mistake. So I'm gonna erase. F is the one that has phase change. Sorry about that. Okay, so if we're doing H, H is 70 weight percent and it's 100 kilograms per minute. So we're gonna have 70 kilograms per minute of H. Its liquid heat capacity is 2.4. And then it's again going from 110, going to 110 from 20. So now we can account for F, which is our stream that has the phase change. So our flow rate of F is 20 weight percent times the total flow rate in that incoming stream of 100 kilograms per minute. So that means our flow rate of F is 20 kilograms per minute. Okay, and then we have this whole term in the middle. So our CP of F as a liquid we can find here. It's 1.6. And then as a liquid, it's going to 105 from 20. It's also vaporizing. So delta H of vaporization is here. So it's 380. And then now as a vapor, it's going to go from 105 to 110. So we can find our vapor heat capacity here. It's 1.2. And we're going to do 110 minus 105. And now, like I mentioned, all of these terms should be positive, so we can double check that that is the case, and it is. So all of the delta T's are positive, and then our delta H of vaporization is positive. So that means all these terms are positive, and we'll get a positive Q heater, which is great. And when we do that, just plug all of this into our calculator, we get 27,360 kilojoules per minute. Okay, so that is all there is to it for this problem. I think this kind of problem is pretty fair game, and by the time you get to, energy balances on reactions and more complicated systems, I hope that this kind of energy balance will be pretty automatic and rote for you. So it doesn't have to be right now, but I would definitely practice until you feel comfortable with this, and definitely feel free to ask us questions if there's anything you're confused on. Okay, so that's all for the energy balances review part of this discussion section. So I'm going to stop this video. I'm going to upload this video, and then separately I'll upload a video on phase diagrams that you should also watch. So the participation points part of this discussion section will happen in that second video. So make sure you watch that. But this is just to let you, if you prefer to watch one of these videos today and you want to watch the next video tomorrow, whatever works. I'm going to make the participation points due at the end of the day, Friday. So as long as you watch that second video and submit your participation assignment by the end of the day, Friday, you are good to go. Okay. Please ask on Piazza if you have any questions.